What did we learn last time? Don't look in your notes, just try and tell me from memory. Yeah, so we learned that we can define this thing called an integral on a curve inside the complex plane. And we learned it's well defined, it's meaningful, it's independent of our choice of parameterization of the curve. And we learned that we can apply the fundamental theorem of calculus to it. And the reason that we do this, the reason that we learn to integrate along curves in the plane is because we want to have the fundamental theorem of calculus. The fundamental theorem is implicitly a one-dimensional idea. Okay, so we've got this apparatus and has some natural corollaries. So here's the first corollary. Suppose gamma is a closed curve in omega, where omega is an open set and suppose f from omega. So from now on, whenever I talk about omega, we're always going to be talking about a subset of the complex plane, so I'm not going to say that explicitly, is holomorphic. And f has a primitive on omega, then integral around the closed curve gamma for z dz is equal to 0. Okay, tell me why. Yep. So, why so? Since gamma is closed, whatever start point we choose, that's also the end point. So if this is the start point, z0, it's also our end point. So by the fundamental theorem, so I'm going to write fundamental theorem of calculus, but the fundamental theorem of calculus in the complex plane. We have that integral around the closed curve gamma f of z dz is equal to f of the endpoint z0 minus capital F of the start point z0, which is just 0. Yeah? Yeah. So if we have a primitive and we integrate around a closed curve, then it's definitely got to be 0. Yeah? And we don't need to talk about parameterization because we proved the fundamental theorem just in terms of having any curve, yeah, and any start point z0 and any endpoint z1. Yeah? Prove the fundamental theorem in these terms, and I'm just applying it, except now the start point and the end point's the same because it's a closed curve. Yeah, cool. So that's what we know already. Another corollary. Suppose F is hollow on connected set open set omega and F prime is equal to 0 on omega. Then F is constant. Okay, so we know this very well from calculus in one variable. It's almost immediately pictorial fact, right? If we have a differentiable function and the derivative is 0, then the function has to remain constant. Yeah. Now in this case, it's less visualizably immediate. However, it is immediate from the things that we know. So someone else, let's spread around the answers. Tell me why this is a true fact. Why is this something we know? Okay, let me give you a hint. So go ahead. So let's pick any 2 points. Z0, Z1 belong to omega. Go ahead. Since it's connected. Because you people proved in homework that if it's connected, it's path connected, there exists a path. Gamma connecting. Z0 and Z1. Okay, keep going. So let's draw a picture. So we have our omega. We've picked a couple of points, Z0, Z1. Sure enough, there's a path that connects them. Yeah? This path is gamma. Keep going. Obviously, it's going to use the fundamental theorem of the calculus in the complex plane. Yeah? Perfect. Yep. There we go. And easy. There we go. Since f prime 0. Cool. So we have this fact that is very easy in calculus. A one variable is also true here. If we have a function whose derivative is constant, then, so again, function's derivative is 0, then it is constant. Yeah? Cool. All right. So, nice corollaries of this fact. Let's erase the board and start with the next theorem, which is, okay, this is Goursat's theorem. I'm going to try and spell Goursat correctly. Okay, suppose omega is open, so we're always going to take an open set just to give ourselves a bit of space to work in. And F is holomorphic on omega, and T is a triangle. Where, so the triangle is, for our purposes, it doesn't have to be right angle, it could be any type of triangle. These three lines like this, okay? So it's not the solid shape, it's the boundary of this shape that I've drawn here, yeah? So suppose T is a triangle where the triangle is contained within omega. Then the integral around the triangle of f of z dz is equal to 0. Okay. Proof. So we've learned already that if it has a primitive and we have a closed curve, then this integral is 0. Now we claim it's true just for an arbitrary triangle. Okay. So this is how we're going to figure this out. So let's draw a reasonably big triangle like this. So this is our triangle. We're going to do this procedure of cutting up this triangle into 4 sub-triangles, and we do it the following way. We're going to take each side, and we're going to go exactly halfway along each side like this. And then we connect up these guys. Like this, and we get 4 triangles. Yeah? And notice about these 4 triangles, so it's probably not that perfectly clear because my triangles are imperfect, but they're all exactly the same size. Okay? In particular, if we do this subdivision, so suppose we go from T, and then we go to this next generation, T1, T2. Actually, I'm going to use T1 and T2 later, so let's not call them that. Let's call them S1, S2, S3, and S4, where this is S1, S2, S3, and S4. Yeah. Then, because the side lengths of each one of these guys is exactly half the side length of the parent triangle, yeah, we know that the following is true. So notice that the diameter of any one of these children is exactly half of the diameter of the parent. For I is equal to 1, 2, 3, 4. Yeah? It's kind of geometrically obvious fact, even though my picture doesn't show it correctly. Yeah? Because the diameter is just the length of the longer side of the triangle. Yeah? Cool. And the second thing to notice is that the perimeter is also exactly half, because the perimeter of each triangle is just the sum of all 3 lengths, yeah, of all the lengths of all 3 sides. And each side of the children, of each side of every child is exactly half the length of the side of the parent. Yeah? So the perimeter of each child is exactly half the perimeter of the parent. Yeah? Give me a thumbs up if you agree with everything so far. Good. And so I'm going to write perimeter as just per. SI is a half of per of the parent T. Again, for I equals 1, 2, 3. Yep. Cool. So I'm going to do this procedure of cutting up triangles in this way. So suppose the theorem is false. So suppose for triangle T, we have that the integral around T f of z dz is not actually equal to 0. Yeah? Then we're going to take our triangle T, I'm going to repurpose this picture, and now we're going to actually, let's call it T0. And now we're going to form children. Okay. We're going to cut it into 4 in this way. Yeah. And let's call the 4 children T tilde 1, T tilde 2, T tilde 3, T tilde 4. Yeah? Then, notice that if we take the integral of T0 of f of z, dz is equal to the sum from I is equal to 1 up to 4 of T tilde I f of z dz. Let me show you why. Because what does it mean to integrate around a curve? It means we take an orientation, right? And for a closed curve, we will be taking the anti-clockwise orientation by default. Okay. Like this. Yeah, that's what this means. This is what this means, right? And if we do the integral of each one of these children, let's see what happens. Take a different color. So we have, it goes like this, like this, like this, like this, like this, like this, and now it's like this, like this, like this, like this. That's what this guy gives. This guy gives this. Let's do this guy here. So we have going inside like this, like this, like this, like this, like this, and finally this guy around like this. Okay, so what do we do with these guys? Well, when we have a piecewise smooth curve, we just integrate each curve separately, put them all together. Yeah. So if we are integrating around T1, we do whatever we want to start. We go here, this guy plus this guy plus this guy. Yeah. T2, we go this guy, this guy, this guy. Yeah. T3, we go this, this, this. T4, this, this, this. Yeah. But notice on these internal lines here, we are going over them twice. Yeah? We're going over them twice, and we're going over them in different directions. Yeah? This internal line, we're going over this way as we go integrating around T2, and we're going this way as we integrate around T3. Yeah? So for this internal line, we are going from this point to this point, and from this point to this point. Yeah? So in other words, we are integrating along the same line segment, except the orientation is reversed. Yeah? And we know, we proved it last time, that when we reverse the orientation, we have exactly minus the integral. Yeah? So when we break up this, or when we consider the two parts of going across this line, they will cancel each other out. And this is a principle we'll use over and over again. Yeah? So if I write this out formally, it's a little bit lengthy, but I could just give this side a particular name, right? And then writing the integral along this side, it's going to occur another time, except going the opposite direction. Yeah? So I'll be adding a path, let's say W, plus a path W minus, which will be 0. So the contribution from this line is nothing. Are you all with me here? Okay, super. And the same for this. We're going in opposite orientations and opposite directions across this line. We're going down and then we're going back up. Yeah? In the process of summing all of this stuff. Yeah? And then this and this. Yeah? So if we just see the stuff that was remaining after we add all these pieces together and take away the cancellations, we have going along here, 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 which is exactly the same as going around the T0 itself. Yeah? You see what I mean? So this is a true fact. Yeah? This is the kind of argument we'll use a lot going forward. So this is true. So if this is non-zero, if it's non-zero, then we're going to have at least one of these guys is going to have absolute value at least a quarter of this. Yeah? It's because, so if we take the absolute value of this thing, T0, f of z dz, it is less than or equal to the sum from I equals 1 up to 4, the absolute value of the integral around these guys, Ti of f of z dz, just by the triangle inequality. Yeah? So at least one of these numbers is to be at least a quarter of this. Huh? Right? So for one triangle, or for one child, brackets child, And it could be t tilde 1, t tilde 2, t tilde 3, t tilde 4. We don't know, we don't care. But one of them, let's call it T1, not with a tilde, now we call it T1. We have that integral of T1 f of z dz, absolute value, is bigger than 1 over 4, the absolute value of the integral of this thing. Yeah? Cool. And then you can guess what's going to happen. So now we are going to do the same game inside our child T1. So let's say this guy here was T1. Yeah, why not? Let's say this guy here was T1. Too much ink to really erase. Well, okay, it's a bit smudged. So if this guy here was T1, then we're going to cut this guy again into 4 subpieces. This, like this, like this, yeah? And we're going to find the child which has at least a fourth of the absolute value of the integral of T1. By the same argument, exactly the same, yeah? Cool. So we can continue. Continue like this. Find sequence of triangles. Oops. Now we're going to have to do some notation to be strictly accurate. So notation. So I'm defining the triangle to be just this 3 line segments. Let's define, oh damn it. Let's define conv of any triangle Ti to be the solid triangle. So it's a triangle plus interior. So Ti union interior Ti. By interior, I mean every point inside the triangle Ti. And I write conv because it's the convex hull of these 3 lines. If you guys have learned what a convex hull is, maybe do this if you don't know what that means. Okay, okay. The convex hull is just, if you have some sort of a set, whatever, and you take any 2 points inside the set and you take the line connecting it, yeah? And you take the union of all the things you can, all the lines you can get from connecting it, yeah? Then that thing is the convex hull, yeah? Yeah, so the convex hull of a circle, for example, is just the solid ball, yeah? That's the convex hull. So the convex hull of our triangle is the solid triangle, yeah? So that's why I write conv, okay? It's something, it's a very useful concept, the convex hull of stuff. You'll see it many times going forward. Okay, so we find a sequence of triangles, okay, and they're all contained within each other. The reason I define this is that, the reason I do this is because in order to say explicitly what contained within each other means, I have to use this notion. So where the convex hull, conv of Ti plus 1 is contained within conv of Ti for I equals 1, 2, 3, and so on. And we'll have this relation holds iteratively, which I'll put down on the board after I raise some space. Okay, let's get back to work with this. So what do we got? Let's draw a picture. We have a parent triangle like this, Okay, and we've cut it into 4, and then this guy gets cut into 4 again, and so on, right? So the way we've chosen them is so that the absolute value of Ti dz is always bigger than a quarter of the parent, right? Yeah. So in particular, if we take the absolute value of this guy, it's bigger than 1 over 4 to the I, the integral absolute value of our original. Yeah? Yeah? Just iteratively applying this one. Yeah? So T1 is bigger than a quarter of this one. T2, start again. Yeah, T2 is bigger than a quarter of T1, so it's bigger than 1 over 16 of T0. Yeah? And so on. Yeah. Okay, cool. So that's a true fact. Yeah. And because we're going to actually, no, let's not introduce more notation than we need. Let's leave it like this. Okay. So we have this true fact. Yeah. Now, if we consider a collection of triangles and their interiors, in other words, the convex hull of them, of Ti, they're all nested inside each other, right? Each guy is inside the parent, yeah? So take, let's say, Zi belonging to this. So these things are closed sets, right? Yeah, their diameter is going down to 0. Then Zi forms a Cauchy sequence. Right? Because we can guarantee that Zn minus Zm is less than any small number we like, right? Because Zm and Zn are inside the smallest of M and N triangle, yeah? That's kind of awkwardly expressed, yeah? I don't want to write too much stuff though. So if n is less than m, then both Zm and Zn are inside triangle Tn, yeah? Yeah? And the diameter of Tn is going down to 0, yeah? So we can guarantee that Zn minus Zm is as small as we like, so long as n is big enough, which is exactly a Cauchy sequence, yeah? I will put more details though if you want. So do this if that's not completely clear. All right, everybody's happy. All right, so this is a Cauchy sequence. So it has a limit. So let zeta equal the limit as I goes to infinity of Zi. Yeah? And what do we know about zeta? So zeta belongs to every single triangle, or at least the convex hull of every single triangle. Zeta belongs to the convex hull of Ti. Oops, I said zeta and I wrote Z. For each I, right? Because they're all nested inside each other. We've taken Zi inside the convex hull of Ti, right? Yeah. So whichever I you want, Zi plus 1 is inside this, Zi plus 2, and so on and so on and so on, right? So from that point on, it's a sequence inside this guy, and this guy's a closed set, right? This guy's a closed set. So its limit will be still inside here. Yeah? And that's true for every single I. Yeah? Everybody, give me a thumbs up if you'll believe me with this. Super. Okay. So zeta is actually inside the infinite intersection. I'm wondering if I is a good letter for you. Is I okay, or would you rather something else? Can you see I? I can use K, for example. Let me change to K, because I feel like this might be better. Is this better? Yeah. So this guy is in the intersection of all of these guys, the convex hull of the TK. Cool. And since our triangle is a closed set inside an open set, this guy is inside our open set omega. Yeah. And therefore, it's a point where the function is differentiable. Yeah. And f is differentiable at zeta. Yeah. Cool. So that means that if we consider f of z minus f of zeta over z minus zeta is equal to this number f prime of zeta plus some error function, which we're going to write as following Stein's notation choice, phi of z minus zeta, where this error function phi, actually, since it's an error function, let's just call it e. No, I'm not confused. Exponential. Let's call it phi, where limit as h goes to 0 of the absolute value of phi. So phi is a complex valued function from the complex plane with this thing. Yeah. So we can unwrap this, and what do we have? We have that f of z minus f of zeta is equal to f prime of zeta z minus zeta plus z minus zeta times this guy here, like this. Yeah? Cool. And what does that say? Well, let's put it completely on this other side. Let's write this. This is f prime of zeta z minus zeta plus f of zeta, and then this error term here, z minus zeta phi of z minus zeta. Okay, look at this stuff here. Look at this stuff in this box. What is this thing? What is this thing if you saw this in a different analysis course? Where is this kind of thing familiar to you? Correct. Indeed, and what is another name for the first two terms of the Taylor series? You're not off at all. Can anybody add to that? Okay, let me give you a hint. What are we doing when we draw pictures like this? Now, imagine we're doing just calculus now. What are we doing with stuff like this, right? Like this line here. It's the tangent line, right? It's the tangent line, yeah? This is the tangent line, and shall I call the T line? And people know that the T line is this thing, all right? So in calculus, we call this a linear function, unfortunately, but it's not strictly speaking linear because it doesn't go through zero, it's affine. But we call it linear, so Jaime, you were right when you said this is linear part, if that's what you mean, if that's what you meant. But it's strictly speaking affine is this thing here, which is indeed the linear part, and then this constant minus a f prime of a plus f of a. Yeah, and it's this function that does an incredibly good job of approximating this thing around a. Yeah, and the whole point of this concept of differentiability is that the error between the function and tangent line is very small compared to a. Yeah, which is what we see with this thing here. Yeah. This is what we see with this thing here. So the error with this thing is going down to zero as z gets closer and closer to zeta. So the error is small compared to this quantity here. It's a much smaller quantity than this thing. Start again. This thing is much smaller than z minus zeta. So if we do this in the complex plane, then this thing would be zeta, and we'd take any z inside some small ball. Yeah. And we would have that this thing here is the dominant term, yeah? And then this thing is something small compared to this radius here, yeah? Because this thing is comparable to the radius, and this thing is a small number, yeah? Yeah? So that's an exact analog of what's happening on calculus, right? So in calculus, if you teach calculus, which you all do, and you'll do a lot in the future, you'll talk a lot about how the difference between the tangent line and the actual function is really small compared to this interval you're interested in. Yeah? Yeah? That's what you see from the picture. Calculus is nicely visualizable. Now we have the analogous thing here. We have the affine term here. This is the affine term. Zeta is fixed. This is fixed. So the linear part is z times this thing. Yeah? This is the affine part. This is the equivalent of the tangent line in the complex plane. Yeah? And this is the error, which is small, which is like this gap here is this error. Yeah? You see what I mean? So if we fix some little sort of delta ball like this, yeah, then this thing will be a lot smaller than delta. It'll be delta times this small quantity here. Yeah? Whereas this thing is some affine mapping where this thing is moving of order delta, right? This thing is moving of order delta. So we have the constant part, and we have this thing times z, and z is moving in a ball of size delta. So this is something which is moving of size delta, and this is an error way, way, way smaller than delta. Yeah? Okay, and that's important going forward. But I want to say that anyway because the analogies between calculus and complex analysis are all going to happen all the time. It's the same subject, except it's doing calculus in the complex plane. So your concepts from calculus you can transfer directly here. We have differentiability. We have the same algebra, the same algebraic properties of numbers, and use your intuition, your knowledge to make sense of this stuff. Directly translatable. In fact, as you learn more higher analysis, we have exactly these things occurring, these concepts occurring very powerfully in much more general situations. This is something called linearization. We linearize PDEs and many other nonlinear problems. We turn into much better, easier manageable linear problems by exactly doing something like a tangent line in higher dimensions, infinite dimensions. All right, back to this though. So we have this is true. This is our tiny, tiny error. This is really what this guy is behaving like. This is the main thing it's behaving like, and this is a lot smaller, right? This is a lot smaller. Yeah? What we're going to do is we are going to integrate around one of our small triangles because we have that our zeta is inside the triangle, right? So we're going to take one of our triangles, TI. Zeta, it could be on the edge, who knows, but who cares? Let's just put it here because it's easier to draw. Yeah? And then we're going to use this fact to see or to estimate what the integral is. Yeah? Cool. All right, so if we integrate around triangle TI of f of z, dz, then it's going to be the integral of this part plus the integral of this part. And again, zeta is just fixed, right? Plus the integral of this thing. All right. Tell me about this part here. Tell me something about this. What kind of function are we integrating here? What kind of function is this? It's affine, right? And what are we integrating it over? What set are we integrating? We're integrating over this triangle T, yeah? Which is a nice closed path, yeah? Yeah? So what would you expect this thing to be? What do you expect it to be? 0. Why 0? So give me another reason why it's 0. When do we know that? Maybe because it's a primitive. Does it have a primitive? If I give you, so forget about the specific details, right? This is, as you say, an affine function. This is a function of the form a, z plus b for complex numbers a, b, right? Yeah? Do you believe such a thing has a primitive? Yeah? What would be the primitive of such a function? What could we differentiate to get this thing? Yeah, I'm trying to erase, so sorry for the rattling sound. So if we differentiate this, a thing like this, az squared over 2 plus b over z, then it does indeed give us the thing that we want. Yeah? Because we know how to differentiate polynomials, we learned about it, and it's just this. Yeah? Cool. So this thing indeed has a primitive because, again, zeta is fixed. So this thing is exactly of the form of this, yeah, but just for different complex numbers a and b. So this entire thing just vanishes, right? This thing is just equal to 0 because we learned that if we integrate something with a primitive around the closed curve, it's just 0. Yeah? Cool. So we just have this. Sorry, we just have this. No? We just have this. No? Cool. And now let's try and estimate it in our minimal amount of space. So the absolute value of ti f of z, this thing, is less than or equal to just the absolute value of this thing. We're going to put the absolute values through this guy. Well, actually, let's not do that yet. Let's take the absolute value like this. Z minus zeta phi of z minus zeta dz. Yeah? Cool. What tool do we have to help us estimate this thing? What did we learn that will help us estimate this thing? It gets small as z approaches zeta, right? Yeah. And we also know that if we have an integral, this is something else we proved last time, if we have an integral across some line, yeah, then that thing is less than the length of the line times the supremum of the function over the line. Yeah? Yeah? So then this thing is less than the supremum over ti of the absolute value of this thing, z minus zeta times phi of z minus zeta. And then just the length of this path, which is just the perimeter, right? It's just the perimeter of the triangle. So of ti, yeah? And as already pointed out, this quantity here is less than the diameter, yeah? And then this thing is pretty small, right? This thing is pretty small, yeah? And this thing can be as small as we like by insisting that I promised to change to k and I did I again, sorry. Insisting that I is as big as we like, right? Because as z gets closer to zeta, then phi goes down to 0, yeah? So differentiability, that's what this thing is, yeah? So this thing we can make as small as we like, yeah? So if we choose any epsilon we like, we can find an I such that this guy here is less than epsilon for every I bigger than the natural choice of I, yeah? So then this stuff is less than epsilon times the diameter of ti, the perimeter of ti, so for all I, let's say bigger than some, let's call it m, which is depending on epsilon. Yeah? Cool. All right, so we have this upper bound here. So it's very tempting to try and put everything on the same board because we have exactly the estimates we need. Okay. From this stuff, what do we have? We have that, so this thing star. So from star, we have that the absolute value of this thing, f of this thing, dz, is less than or equal to epsilon diameter of ti. Let's actually put in what it is already. So we know that the diameter of ti is decreasing in this very specific way. Well, actually, it's not on this board, it's on the last one. Because every ti was the child of ti minus 1, and then the diameter was exactly a half, right? Yeah? Yeah? And the same was true of the perimeter. The perimeter was exactly a half. Yeah? Yeah? So that we have that this guy, the diameter of ti, is 2 to the minus I of the diameter of the original guy, right? Put in capitals. Diam of T0, yeah? And this guy, the perimeter of Ti, is also 2 to the minus I of the perimeter of our original guy. D0, yeah? Yeah? So what is that? That's equal to epsilon 4 to the minus I, the diameter of T0, the perimeter of T0, yeah? Cool. But we have this lower bound too, right? So let's call this thing star. Yeah? Oh, star star, but from star star, so we have this guy is bigger than 1 over 4 to the I, this guy, yeah? So we could directly put this in here, so then we have 1 over 4 to the I of this thing, f of z, dz, yeah? Yeah? This guy, yeah, is equal to this guy, which we found is bounded above by this thing epsilon over 4 to the I, then diameter of T0 times the perimeter of T0. Yeah? And these numbers, diameter T0, perimeter T0, are just fixed numbers, right? We have some triangle, it has some diameter, it doesn't matter what it is, we don't care. Because now these 1 over 4i's cancel, right? Yeah? And we have that this thing is less than epsilon, these fixed numbers, and epsilon is any number that we like. Yeah? Now this is independent of I. Yeah? Which implies that integral of T0 f of z dz is equal to 0. Thank you for this question. So this guy is what we got from differentiability, right? So let's bring it back up here. So differentiability, wrote like this, f of z minus f of zeta over z minus zeta is f prime of zeta, and then this thing, which is the error, which is z minus zeta. Yeah? And then definition of differentiability, as z goes to zeta, this thing tends to this thing, which is exactly saying that phi tends to 0 as z approaches zeta. So I wrote that limit as h goes to 0, where h is a complex number, of the absolute value of this thing is equal to 0. That's the statement of differentiability, yeah? Cool. And this phi, it depends on f, obviously, but it's chosen, it's there. This is just a true thing, it's a function, it satisfies this. Yeah? It's an analytic function, it's a holomorphic function that satisfies this. Yeah? And then this is what we're using right here. Yeah? Because when we take the supremum, then this thing, z minus zeta, this is less than the diameter of the ti, so that's where the diameter comes from. Yeah? As we go integrating around this thing, that's the perimeter, right? Yeah. So we have the perimeter, the diameter, yeah, from this part right here, and then this thing is, as z is over ti, and zeta is inside ti, right? So this is a very small distance right here. Yeah, this is a small distance. So we're taking we're taking z on this triangle here. This is where z is, yeah? And it's very close to zeta. Yeah? And as I increases, then this diameter gets smaller and smaller. So then this thing right here is going down to 0, depending on I. Does that make sense? Perfect. Thank you. Thank you for the question. That's the point of this. Please stop me and ask me questions at any point. That's why we struggled with this technology for 2 weeks before we finally have something that works. So yeah. Please do that. All right, good. Let's recap the steps. What did we do? We took a triangle, so this is kind of key steps, and we observed that we can keep cutting it up, yeah, into 4, where if we call this 4 that we cut it up into the children have a nice property that the perimeter is exactly half, the diameter is exactly half, yeah? And a further nice property that if we integrate over the sum of the children, because of the internal cancellations, that's the same as the integral over the parent. Yeah? And that's actually the main idea of the proof. Yeah? So if we have that the integral around our original triangle is non-zero, then we can keep finding a child which has at least a quarter of the absolute value of that integral. Yeah? So we have this sequence like this, which bounds below what these integrals have to be. So it bounds below what this is, yeah? But if we take the intersection of all these triangles, there is a non-zero point. We take differentiability, and we write out what differentiability means. Differentiability means we have the function is equal to some affine part and then a small error, yeah? And the affine part has a primitive, so that thing cancels. So what remains allows us to get an upper bound rather well, just in terms of the diameter times the perimeter times epsilon. Yeah? So we put the upper bound we get from differentiability with the lower bound we get just from this choice of picking the biggest subtriangle, the biggest child, and ultimately get this contradiction here. Yeah, this is something which is really, really different than what you might expect, right? This is quite a strangely strong property just from differentiability. We just use the fact that our function is differentiable. This is when we start to see that calculus from the complex plane to complex valued functions is very different. This is a very different story. Differentiability means that if we integrate over a triangle inside our domain, it has to cancel. It has to be zero. And as we're going to see, that has huge consequences. Yeah. So one of the things that you should expect is that on the midterms, I'm going to ask you to prove theorems or parts of theorems. And my claim is that it's not hard to do if you understand them. And what you need to understand from this are just two ideas. Just two ideas. First idea, cutting the triangle into 4 subtriangles. Second idea is using differentiability to estimate above the integral over a small triangle, seeing that a big chunk of it will cancel just because we know that there is a primitive. Just two ideas. And the rest of this stuff is just expressing the consequences of those two ideas. Okay, this is just working through in the language, expressing your thoughts in the language, what the consequences of those ideas are. It's not hard to do this. It's not hard to write out all these details if you have these ideas clear in your mind. Yeah? And that's what I want you to get to. I do not want you to try and memorize this as a sequence of symbols, of statements. Science of memorization will be very bad. That's not what I want. If you produce something that looks eerily like what I produced when I asked you to do something like this in an exam, that's not good. That's not what I want. If you produce something which is written in a completely different notation and it's sort of a different order of the way you do it, but it's clear it's coming from your brain and not from your memory, that's what I want. Okay, so you're going to have to. So all of you on the PhD program, you're going to have to. The idea is you're going to do research, contribute to math, and you're going to have to learn your research areas very well. You're going to have to know the fundamental theorems, the kind of fundamental methods of the areas you work in very well. You're going to have to learn math at a deeper level than you've probably reached already, which means being able to recapture it rather easily just from the basic idea. So this is where you start to try to do this. And it's a good subject to do this because the technicalities are rather easy because these are such nicely behaved functions in many ways that you don't have to worry about lots of things. The proofs are actually rather straightforward. So try to get to this. It's not enough for you to verify oh yeah, that step is correct, I believe him. I want you to be at the point where you can be sitting at your table, whatever, I don't know, watching Game of Thrones and then wonder, I wonder how that theorem works. And then you'll have these ideas in your head and you'll be able to sketch out the proof for yourself. That's what you've got to get to. And that might seem like it's a high bar, but it isn't. It's what you can do. That's what you need to get to. You'll find that if you try and get to that level, you will be able to do it. Yeah. So start practicing now by thinking about these theorems and asking yourself if you know why and trying to prove them, not by looking at the notes, just by thinking about what were the main ideas. Take away the main ideas, keep those in your head, try and recapture the details from the main ideas. And maybe you're not going to succeed, but give it a go for whatever, 20 minutes or something. And only when you fail, look at the details, see how I did it. Yeah. And if you do that a couple of times, you'll find that you can recapture the details for yourself just from these basic ideas. That's what I want you to get to the stage of. It's got to be something in your head and not on paper, not symbols on paper. All right, cool. We've got some more time, just a little bit more time. All right, yeah, I'm going to raise the border and tell you a few more things. Here's a consequence, so a theorem. suppose f from omega into the convex plane is holomorphic, and a rectangle R is contained within omega. When I have a rectangle, I mean these four lines, not the solid rectangle. Then the integral around the rectangle, f of z dz equals 0. Tell me why that's true. Why is this true? Perfect, yeah. So again, we're going to orientate this anti-clockwise. And we can cut into triangles where we go down this way, okay, and then we go back this way. Yeah? Better if I did it in a different color, the other way around. Yeah? Cool. And this is a theorem I'm going to talk about next time. So, suppose we have a disk I'm going to spell disks. I'm going to call it a ball. B contained within the complex plane, and F from the ball, complex plane is holomorphic. Then F has a primitive on the ball. Okay, and what would be a really great exercise, though I can't set it as an exercise because it's kind of it's too hard and it's too easy just to look up, is to try and prove this from the following hint that I will give you. So if we take our ball, okay, since it's a ball, then for any z inside the ball, we can create a line that goes like this, and then up to the point like this. Yeah, we can create such a line. Let's call that line gamma of z. Yeah, for any ball, we can create a line made of these two straight lines that do this. Yeah, and whether we go along and then up, or up and along, turns out to be the same thing by just what we learned over there. Okay, so this is a path like this. Okay, and then claim we have that capital F of z, which is defined to be the integral over this guy of little f, let's do variable zeta, d zeta, is the primitive. Okay, and how would you show that? Well, you'd have to try and understand f of z plus h minus f of z over h, and you'd take the limit as h goes to 0. Yeah? But I claim that from this definition and from what you've learned already, if you look at this quantity carefully enough, you can understand that this thing, as h goes to 0, will tend to just little f, okay? And it'll actually fall out from the pictures if you look at them carefully and you draw them carefully, okay? And this is in Stein. If you do this exercise, then resist the urge to glance at Stein. Just try and figure this out for yourself. try and figure out why this thing, as h tends to 0, is going to tend to f of z as h tends to 0. And if you spend enough time at this, and enough doesn't mean hours, probably might mean hours. Good if it does mean hours. Good to spend hours thinking about stuff. But if you spend time at this, you'll get it. You'll see it. And then you'll understand it a lot better than from listening to me. Okay? So from this hint, if you're starting to enjoy this subject, if you want to get into it, find it better, give this a go. Give this a go. Sweet. All right, that's it for today. Have a great day. See you all on Tuesday. Bye-bye.